Good afternoon, ladies and gentlemen. My name is Dr. Jon Belkowitz, and I am excited, thrilled to give you the next set, the second mix from our PMXDB, our practice mix design book, where we set up customers and clients for you with materials and go through the math, the awesomeness of turning that into a concrete mix design using ACI 211, this guideline for making normal, standard, conventional concrete. And let's just dive into it. So for practice mix design number 2, we've got an 8-inch wide, 8-foot tall reinforced wall exposed to moderate freeze thaw and de-icing. So whether it's infrastructure for a local bridge or infrastructure for a walkway bridge, or something that's used on the outskirts of a building, what we're looking for is a compressive strength of 3,500 PSI for 28 days. A 4-inch slump for our fresh properties. We've got a minimum cementitious content of 517 pounds per cubic yard. And we want to design for a cubic yard and 1.2 cubic feet as if we're going to do this in the lab. We're using a Coarse river rock 3/4 inch maximum sized aggregate with an absorption of 0.9%, a moisture content of 1.1%, specific gravity of 262, and a dry rotted unit weight at 97.2 pounds per cubic foot, all of which we're going to need for our design. Continuing on to our natural sand, we have a fineness modulus of 2.73, a specific gravity of 2.60, an absorption of 1.0, and a moisture content of 5.8. It sounds as if we've got a natural sand here and not a manufactured sand, and the blaring difference would be, normally you would see a higher absorption. Okay, so admixtures, supplementary cementitious, we'll leave that over to the end user and the local region. None are specified. But let's dive into it. We're getting into ACI 211, proportion for normal, heavyweight, and mass concrete. Our first indicated or given information that we're going to use in table 6.3.1 is this tall reinforced walls. And under our recommendation slump for various types of construction for reinforced walls, foundation walls, and footings, and then also for reinforced walls, we see a maximum of 3-inch, a minimum of 1-inch. Then the second suggestion is a maximum of 4-inch, a minimum of 1-inch. Since it says just a tall reinforced wall, and it doesn't state whether or not it's a reinforced foundation wall, we're going to go for just a reinforced wall with a maximum or a slump of 4 inches. Okay, so that's step 1, so let's go ahead and write that down, 4 inches. Then we're going to go over to step number 2, which is table 6.3.3, my lucky number. And we're going to use our maximum sized aggregate here, which is 3/4 of an inch. And then we're going to drive that down to our slump. And because we've got moderate freezing and thawing, we want to drop that down to air and train concrete. So we've got a 3 to 4 inch slump with a 3/4 MSA. It looks like we need 305 pounds per cubic yard of water. But remember, we're using river rock, and there's a note underneath this table that says rounded aggregate would generally require 30 pounds less water for non-air and trained and 25 pounds less water for air and trained concrete. So we're going to take 305 minus 25, which gives us 280. So that's our ending water for that table, and then go down for moderate freeze and thawing, and we need 5% air. So let's go ahead and write that down. So 5% air, or total water, 305 pounds per cubic yard, minus the note 25 pounds per cubic yard gives us 280 pounds per cubic yard. And then, of course, because we had that 5% air, we're going to need to use an air and training agent. And why don't we go ahead and write that down and assume a half an ounce per hundredweight of an air and training agent. We can use Quizo Air 260. This is not a promotion for that technology. That's just something that just came to mind. But looks like we've gotten everything that we need from step number 2 under table 6.3.3. Let's go to 6.3.4a for step 3. And our compressive strength, if you remember for our air-entrained concrete was 3,500 PSI at 28 days. Because it's for a reinforced wall, I automatically went with a water reducer, and I went for a mid-range water reducer, a Darasum 55 made by GCP, or you could use one of the quad products by Crezo since we're already using Crezo Air, but if you wanted to use GCP, I think their air is AT60 or something to that effect. But we'll go for 12% water reduction using the Darasum 55, somewhere around 4 ounces per hundredweight. So 12% water reduction is going to give us somewhere around 245 pounds per cubic yard of water. And it's not going to be exact, but that's where we want to shoot for. And if we use our minimum cement content, 246 divided by 517, you get 0.497 for our water to cement ratio. And if you look over at our table 6.3.4a, 3,000 psi we want a 0.59, 4,000 psi we want a 0.48, and right now we got a 0.497. So that's in the ballpark of where we want to be. If we average those two out to get a 3,500 psi, we're going to be a little bit higher than that. We jumped over to 6.3.4b to double check that for all other structures we're 0.497, and this is something that you have to have. It can't be higher than this for the structures that are wet continuously or frequently and exposed to freezing and thawing, and we're below that 0.50 or 0.497, so we're going to stick with that. With that, we're going to go ahead and move over to figuring out the amount of coarse aggregate. So we've got our table 6.3.6 that we've jumped to. They've given us a fineness modulus of 2.73. We also have a dry unit weight at 97.2 in our maximum sized aggregate. So what we could do is, from our FM calculation, there is no 2.73, so we can use linear extrapolation with our values given are 2.6 to 2.8, the number we have, which is 2.73, and the numbers that they gave us to determine what is our actual X value. And this is the math that goes into it. Or you can say, hey, looking at this value, the 2.73 is either closer to a 2.7 or 2.8 or 2.6, and evaluate the number from there, because the reality is these mixes that we're doing are just benchmark mixes. We need to make sure everything yields, and our accuracy within our plant is not going to be to the accuracy of our math here. It's actually a little bit more coarse, but again, using that linear extrapolation, we get X equal, or our volume of oven dry rotted coarse aggregate per unit volume of concrete for different fineness modulus of fine aggregate is going to be equal to 0.63. Now, while it's awesome that we have that number is meaningless until we multiply it by our other values. So this 0.63, when we multiply it by our unit volume, our 27 cubic feet per cubic yard, and our dry rotted unit weight, what it ends up calculating for us just through our unit conversion here is our pounds per cubic yard for our coarse aggregate. And with the 97.2 pounds per cubic yard, or pounds per cubic foot for our dry rotted unit weight for our coarse aggregate, we get a total of 1,653 pounds per cubic yard that we're going to use for our coarse aggregate for our concrete, which is exciting. Because now what we've done is we've created the background information that we need to determine how much value we've used or volume we've used up for 27 cubic feet in a cubic yard. And then we can go ahead and back calculate how much volume we have left of our sand to go ahead and determine the weight that we need for our sand. So we do just that with our water. We divide our 246 pounds per cubic yard divided by 62.4 pounds per cubic foot, giving us 3.95 cubic feet, our volume of water in our 1 cubic yard of our concrete composite. And then we do the same thing for our cement, our 517 pounds total cementitious, divided by our unit weight, which is our 62.4 pounds per cubic foot, times our 3.15 for our specific gravity, to give us 196.6 pounds per cubic foot for our cement. And our 517 divided by our 196 gives us this 2.63 cubic feet for our cement. And we do the same thing for our coarse aggregate, that's 1653 divided by our 62.4 pounds per cubic foot by the specific gravity of our coarse ag, which is 2.62. And that gives us a volume of 10.11 cubic feet. We need our air content, which we know is 5% of our 27 cubic feet in our cubic yard, which is 1.35 cubic feet. When you add that all together, you get a total volume of 18.04 cubic feet. Now remember, we're starting out with 27 cubic feet, so we have left over 8.96 cubic feet for our fine aggregate. And what we do with that is we multiply that 8.96 times our specific gravity of sand and our 62.4 pounds per cubic foot to give us 1,453 pounds per cubic yard of sand. Now, please bear in mind, this is not the weights with the moisture and absorption taken into account. What we have right now here is our generic, our subtotal, if you will, before we take into the account of taxes, if we're going to, put an analogy to shopping. But now we've got to take into account those taxes, those moisture contents, and the absorption. To do that, for our coarse aggregate, for our wet, we multiply that 1653 by our moisture that we had, which was 1.1% for our coarse aggregate plus 1, and we get 1,672 pounds per cubic yard. That's our coarse aggregate that's laden with our 1.1% moisture. We do the same thing for our sand, remembering that it had a 5.8% moisture. So we do our 1453 by 1.058, which gives us 1,538 pounds per cubic yard of water. Of moisture-laden sand that we're going to batch out per cubic yard. Now, to get our batch water, because our design water with our Darasem 55, our water reducer, was 246 pounds, but now we have to take into account the water that the rock and sand are bringing. And it's not just the total water, it's the free water that's sitting on the surface. We're not taking into account that water from absorption. So what we do is we subtract our moisture from or by our absorption. So before we had 1.1% moisture, but some of that moisture is going to be monopolized by absorption. So there's only really 0.2% of that moisture that's going to be free water. So we multiply that by our total weight. We do the same thing for our sand, which is that 5.8 minus 1% absorption. And what we get with that, subtracting that from our total design water, is a batch water of 173 pounds per cubic yard. So now, bearing in mind that we that's a cubic yard, now we got to bring that down to a cubic foot, which our cubic yard, we have a water of 173 pounds, or cement of 517 pounds per cubic yard, our coarse ag of 1672 pounds per cubic yard, and our fine ag of 1538 pounds per cubic yard. All of that is per cubic yard basis. Now to get to our 1.25 cubic foot, we divide that by 27 and then multiply that by 1.25 cubic feet to get 8.02 pounds per our batch for our water, 23.9 pounds for our cement, 77.4 pounds in our coarse ag, and 71.2 pounds for our fine ag. Now, the amount of chemical admixture is going to vary. We said for the 4 ounces, for the Darasem 55, we're going to use 4 ounces per cement hundredweight, 4 fluid ounces per cement hundredweight. So we take 4.0, multiply it by our cement hundredweight, which is 517 pounds per cubic yard, divided by 100, which gives us 4.0 fluid ounces per hundredweight, multiplied by 5.17 hundredweights, gives us just over 20 fluid ounces per cubic yard. But remember, we need to do that in our batch form. We'll say 20 fluid ounces divided by 27 cubic feet in a cubic yard, multiplied by our batch size, our 1.25 cubic feet, gives us 0.93 fluid ounces. And then we multiply that by 29.57 milliliters per fluid ounce to get 27 milliliters per our batch. And that's how we're going to measure it out for our batch size. We do the same thing for our air. Our Crezo Air 260 at half a fluid ounce per hundredweight, or our GCP product. I believe it's called the AT60. If I'm wrong, I apologize. At a half ounce per hundredweight, we'll multiply that by 5.17, which gives us 2.6 fluid ounces per cubic yard divided by 27 to give us per 1 cubic foot. Multiply that by 1.25 cubic feet, which is our batch size, and of course converting it to milliliters, which is multiplying it by 29.57, and now we've got 3.5 milliliters. Okay. Whew. That was a lot. Now, normally what we would do with this mix is we wouldn't just send this out. We would go ahead and trial it in the lab. You know, we've got Bookcrete. Then we need to go after LabCrete, try it out once or twice, maybe more than that, maybe do a redesign, because this is only a benchmark mix. This doesn't take into account the certain physical properties that you just don't see on paper. So there is going to be a trial and error portion, and eventually there's going to be a real crete where we go through a technical transfer to bring this up to the field, and there's going to be even more adjustments from there. So hopefully you learned something. Let us know if you got any concrete questions, concrete concerns. Don't forget to like and subscribe. Ding that bell for notifications. Go concrete! Beat asphalt.